I think the laws of physics are not laws. They are a mathematical construct that we use in order to describe the world around us. They work for us at the moment. They may no longer work for us 100 years from now or 1,000 years from now.
Okay, so we like to call them regularities that we now see irregular, which might have some changes in the future, but that reflects on our understanding as opposed to the regularities themselves.
No, it's something more basic. Physics is a language that we use to describe the world, just as we use language to tell stories.
Welcome to Close to the Truth. I'm speaking with Astrophysicist Or Graur about his expansive new book, Galaxies, which I loved, and his last book, Supernova. Galaxies being the core of cosmic structure, and supernova, which create the heavy elements needed for life and which give us standard candles, which we'll discuss, to measure cosmic distances. Welcome, Or. It's great to meet. Congratulations on Galaxies. As I said, I loved it.
Thank you, Robert, and thank you for having me on the show.
It's a pleasure. Now, we're going to discuss Galaxies in great depth. I learned a lot, and I look forward to discussing it. But let's just start with some of the breathtaking discoveries of the James Webb Space Telescope, literally breathtaking. The images, the data, the gravitational lensing, and their implications for cosmology. We see certainly early galaxies, larger, earlier, more structured, more numerous than expected. I think the latest is galaxies at less than 300 million years after the Big Bang. 290 was the last one I saw. That's within 2% of the 13.8 billion years age of the universe. Early black holes, larger and more expected. Of all these observations, which are your favorites in the sense of conveying surprising data?
I would say it's the things you don't hear about, at least not yet. I have a colleague, Sandro Tacella, who's one of the big collaborations searching for the earliest galaxies. And I was in his office. He was showing me images from the James Webb Space Telescope. And first of all, the first impression I had was that I was still looking at images from the Hubble Space Telescope. They look very similar, and you have to flip a switch in your mind and remind yourself that the galaxies you're looking at, which look nice and resolved just like you would expect from the Hubble Space Telescope, are much farther away than the same types of galaxies you would see in Hubble images. And the other thing he showed me was there were all these little green dots in the image, which at first just looked like noise. And then he pulled back and pulled back and pulled back until he showed me a huge green blob, which was a very nearby elliptical galaxy. And it turns out all these little green dots are individual stars from that galaxy. And that is something you do not see with the Hubble Space Telescope. Not like that. So, that's just speaking to its observational capabilities.
The galaxies in which you resolve those individual green stars, what was the approximate age of that galaxy?
Oh, that was a nearby galaxy. So that was, that's a galaxy that's been around for billions of years. That's not the kind of galaxies you were aiming at.
Yeah, but that in that galaxy, you never were able to resolve individual stars with Hubble. That's the point. Right?
Yeah, exactly.
So what about all those, all the stuff that makes the sensational headlines about disrupting the standard model because these galaxies didn't have enough time to form, and then there they are, and massive black holes that shouldn't have been able to form within hundreds of millions of years, that should have taken longer than that, but there they are.
Well, when it comes to that, I would say let's wait a bit longer. The James Webb Space Telescope has only been operating for about a year and a half.
Mm-hmm.
And people are now analyzing the first round of images. And so I wouldn't put too much emphasis on what's coming out now. I would wait. Another year or two until we get results from several years of observations, several years of analyses, especially by the large collaborations. I would also say that just because we have some observations that challenge lambda CDM, that doesn't necessarily mean that it's broken. I would think of it as pushing on a balloon from the inside, right? You can push on the skin of the balloon. If you push too hard, it will break. Mm-hmm. I'm not sure we're there yet.
Okay, well, that's going to frame part of our discussion, but let me first now give a little bit of a more formal, a brief, but a more formal bio. Or Graur is Associate Professor of Astrophysics at the University of Portsmouth's Institute of Cosmology and Gravitation, as well as Research Associate at the American Museum of Natural History. He specializes in supernova studies, which we'll talk about, and is the author of the book Supernova, as well as Galaxies. Both are from MIT Press. So, we're going to discuss galaxies in depth, but I want to set out what we've started to talk about as kind of an organizing framework, or at least keep in the back of our mind this so-called challenge to the Big Bang cosmology, which is sometimes called the standard model of cosmology, using the analogy for the standard model of particle physics, which has the lambda cold dark matter, as you said, lambda CDM in short, as its framework. So as we discuss galaxies, whenever some data supports the standard model, maybe allude to that, and then we'll see what this is all about. In addition, which we haven't mentioned so far, is the so-called Hubble tension for the rate of the expansion of the universe, with different methods coming out, what some people may think is fairly close, but with the statistical variation so small, the differences seem to be very robust. And some people use this as well to challenge or undermine the standard model. So let's keep both of these tensions in mind as we go through. Does that make sense?
Perfect.
Okay, so let's start with galaxies and just give me some of the overarching fundamental principles of approaching galaxies. Start with the kinds of galaxies.
So there are a lot of different types of galaxies. I think most people will be familiar with spiral galaxies because they're so pretty that they're everywhere on the internet, on our books. So spiral galaxies are, we usually call them disk galaxies because most of the structure is in a thin pancake-like disk with a bulge or a bar in the middle, and the spiral arms develop in the disk. Aside for these spirals, we also have elliptical galaxies, which look like American footballs or rugby balls. There are lenticular galaxies, which look like lentils. There are something in between spirals and ellipticals. There are interacting galaxies, where you have two or more galaxies that are close enough together that they interact with each other gravitationally and then distort each other, rip each other apart into very weird shapes. And then we also talk about the sizes of galaxies. So we have dwarf galaxies, massive galaxies. We have irregular galaxies, which are galaxies that don't seem to have any specific shape. They're just blobs of stars. And then when you start looking back in time, and that's especially where the James Webb Space Telescope will be interesting, we also have the primordial galaxies, which look different than what we see today. So
okay, let's just dig in a little deeper. As you said, spirals are sometimes you called them disks because of the ratio. I think I read in the book where the ratio can be the length to the height as 1 to 100, or 1 to 40, maybe in the case of the Milky Way, but 1 to 100. So that's an enormous ratio difference. And so that indicates that there has to be a reason for that. That's just not a random thing. So what is that ratio, and how did that develop in terms of the galactic formation?
That comes about from the way gas settles into a disk due to angular momentum. So basically, everything in space spins. Earth spins, the sun spins, Earth spins around the sun spins around the center of the Milky Way. And, Earth, the sun, these, we think of them as particles, but they're embedded in gas, mostly hydrogen, some helium, tiny bit amount of other elements. And that gas is also spinning. And that gas is made up of particles, individual atoms and molecules. So we have to go a bit back in time, and we have to understand how exactly galaxies form, it's a big question. The basic idea is that, we'll talk about this more when we talk about the large-scale structure of the universe, but the basic idea is that you have these pockets of dark matter into which regular matter funnels. So you have gas falling in to a pocket of dense dark matter, and inside this pocket, all the gas is falling in from all directions, and when it falls in, it will move in all directions. But due to gravitational interaction, over time, you will get a preferred vector of rotation. Okay, you will get an average, let's call it an average rotation. And at first, what you'll have is a very puffy cloud, which is starting to rotate in a uniform way. And as more and more of the gas and the particles rotate in the same way, this cloud will start to flatten out. Something very similar happened in our solar system. All right, our solar system came into being out of a condensing cloud of gas. In the center of that gas, a very dense ball of gas condensed to form the sun. But the sun was then enveloped by this cloud of the rest of the gas. And out of that rest of the gas, the other planets condensed. And again, they condensed out of what came to be a very thin disk around the sun, which is why all the planets orbit pretty much in the same plane. The actual physics are a bit more complicated, but this is the hand-wavy explanation.
So the same physics that causes the planets in our solar system to be in a plane is the same physics that works on a grander scale, making disks in which you have this very substantial ratio of 1 to 40 or 50 or even to 100.
Yes, there are additional physics at play, but the idea is the same.
Okay. How does shape, you gave us different shapes, relate to age in terms of, as we look back through Hubble and that now JWST?
As I said, it takes a while for a cloud of rotating gas to settle into a thin disk. So the earliest galaxies in the universe, the earliest star-forming galaxies, had thick disks. They had thick, puffy disks. Okay, and it would have taken them a few billion years for the disk to settle into the thin disk structure that we see in nearby galaxies.
And is gravitation the sole reason for its structural development over billions of years, or do some of the other forces have like electromagnetism interactions between molecules have an effect as well.
No, at these scales, at cosmological scales, it's gravity.
Okay, it's basically 100% gravity.
It's basically 100% gravity, and until you get into the physics of specific objects,
Okay.
like black holes and supernovae.
Oh, sure. Okay, so now we've talked about a single galaxy and the different kinds, and now let's expand from that in terms of the structure of galaxies, multiple galaxies, in terms of galaxy clusters. What is that? And then the different categories of size, local groups, superclusters, etc. Give us some sense of that organizational structure.
Okay, so we tend to think of galaxies as isolated islands in the ocean of the universe, but we should really be thinking of them more as archipelagos. Most galaxies are found in groups, where a group is let's say a bunch of galaxies that are tied together gravitationally. Our Milky Way galaxy is part of the local group, which includes a few dozen galaxies. The large galaxies, the massive galaxies in this group are the Milky Way, Andromeda, and the Triangulum. And all the others are smaller galaxies, most of which are satellites of the massive galaxies.
And so order of magnitude between a massive galaxy, we're talking about our local group, Milky Way has 100 to 400 billion stars, Andromeda close to 1 trillion, numbers that I've seen around, but make them more accurate. And then the satellite galaxies, Magellan Cloud, etc., have how many stars? Just give some relative sense.
We like to think in orders of magnitude. So a galaxy like the Milky Way, that's 10 to the 11, 10 to the 12 stars.
So the order of magnitude 10 to the 11th is 10 to the 100, 10 to the 12
10 to the 10 to the 10 to 10 to the 11. The most massive galaxies go to 10 to the 12, a bit beyond. Dwarf galaxies around 10 to the 9.
Okay, billion. Yeah.
So the Magellan Clouds, those are about 10 to the 9. So most, and you can go to the tiniest dwarfs are about 10 to the 6, 10 to the 7.
Okay, so tiniest is 1 million to 10 million or so.
Yeah.
And so those are the orders of magnitude. The tiniest, 1 million to 10 million. The very largest is 1 trillion. Milky Way, 100 billion to 1 trillion, someplace in that order of magnitude. Okay, that's a very good sense. And so in a local group or a galaxy cluster, what's the range of the number of galaxies that would be in and what's the average?
So a group is defined as having up to 50 massive galaxies, and each of those galaxies will probably have its posse of satellite galaxies. Well, how many satellites they will have, we don't know. We're still discovering more satellites around our own Milky Way galaxy, but think in the dozens. Groups that have more than 50 galaxies, more than 50 massive galaxies, those are called clusters. And the largest clusters have thousands of member massive galaxies, where each galaxy has its own satellites. And in galaxy clusters, you also find BCGs, brightest galaxy members, which are the most massive galaxies we know of. These are galaxies with trillions and trillions of stars. Galaxy clusters are the most massive gravitationally held objects in the universe. That's also where you see strong lensing effects, all those beautiful arcs. And galaxy clusters themselves can form superclusters. So we're in the Milky Way. The Milky Way is in the local group. The local group is inside the Virgo supercluster, and the Virgo supercluster is part of the Laniakea supercluster, which itself is a cluster of superclusters.
And so, roughly in each stage of the ladder of expansion, what's the order of magnitude difference in terms of numbers? Start with the local group, and then the Milky Way, and then go up to the Virgo supercluster, and then the cluster of the superclusters. Rough numbers.
Rough numbers, as I said, a massive galaxy will have tens of satellite galaxies. A group will have dozens of massive galaxies. A cluster will have hundreds to thousands of massive galaxies. A supercluster, I don't know how many clusters it will have in it. I would think on the order of tens to hundreds. And then you can build up from that, and you build up and you build up until you get to the large scale structure of the universe, which is also called the cosmic web, where you see all these galaxies and clusters and superclusters arranged in filaments that intersect in nodes around these areas mostly devoid of galaxies. You get this kind of spider web effect.
Yeah, it's a remarkable story to understand that. Okay, let's look a little bit deeper into the internal structure. One of the things that the book pointed out, which I found very interesting, is that stars make up a fairly small part of the total mass of a galaxy cluster. So describe that relationship between what we would think is a minor gas and the stars themselves.
The question to your answer depends on which type of galaxy we're looking at. So first of all, we should talk about the components, what makes up a galaxy. And we should start with the very startling fact, which is that most of the mass of a galaxy is dark. It's in something that we don't understand yet. We haven't been able to isolate it or understand its nature. It's something that interacts with regular matter gravitationally, but not electrodynamically. So it doesn't emit light. That's most of a galaxy. Then we have gas, which, as I said before, is mostly hydrogen and helium. We also have dust, which are tiny molecules that have condensed out of the gas. And then we have stars. Stars are what we see. Stars emit light. And so when we look up at the Milky Way in the night sky, we see the stars. But in a disk galaxy like our own, most of the normal matter is in the gas. In an elliptical galaxy, there's almost no gas. So in an elliptical galaxy, you have dark matter and some stars. So it really depends on which type of galaxy you're looking at.
So let's be clear, using the Milky Way, our galaxy, as the example. We know overall, roughly, and we'll get into this a little bit later, why, that only 5% of the total mass density of the universe is what we call ordinary matter. Another 25% is dark matter, and 70% is the dark energy, and that's a huge thing. So let's put this dark energy aside. So we have roughly 1/7 or so of the Milky Way is ordinary matter, and just 15% or whatever is closest to understand. The rest is dark matter. So of the part that's normal matter, or this 1/7 of normal matter and dark matter, what percentage of that is gas and dust as opposed to stars?
So I honestly don't remember. It's in the book. The numbers and fractions are in the book, but I don't remember them.
Yeah.
That's
I
I
I seem to recall why it startled me is that it was like between 5 and 10% is normal, is visual matter, stars, and that 80 to 90% are the things we don't see, and this is not including dark matter, which, as I said, was very it's fascinating.
what I think is important to take out of this is not really the numbers, but the processes, the reasons for the numbers. So what's important here is that we need to remember that stars condense out of the gas.
Yep.
In a spiral galaxy like our own Milky Way, which is it's forming stars, it's a star factory. Your input, your basic resource is this gas. It's hydrogen. So when galaxies form, like I said, you have gas falling into a dark matter halo. All you have is gas, right?
Mm-hmm.
100% gas, zero stars. And then the first stars are formed. They blow up very quickly. And then the next generation of stars is formed. And so over time, you're converting gas into stars.
Uh-huh.
Okay. Now,
when you say blow up very quickly is defined in millions of years as opposed to billions of
exactly.
years.
Yes.
Okay.
Millions of years is a heartbeat.
Right.
So this galaxy, spiral galaxies, you can think of them as factories converting gas into stars.
Mm-hmm.
At the beginning, this conversion process was very efficient, and star formation rates were very high, and they rose quickly until a period about, 10 billion years ago, during cosmic noon, when star formation rates reached a maximum and then started to decline. So the Milky Way today is not as efficient as it used to be at forming stars, but it still is. It's still forming stars. It forms, I think, about 2 new stars per year. I think I said 1.6 in the book, but let's think of it as 2 stars per year, which doesn't sound like much, right? But we have to remember that the Milky Way has been here for billions of years, and that means that a billion years from now, there will be 2 billion more stars, which is enough to populate an entirely new galaxy.
And each one of those stars may have the disk around it that could form planets, which is another whole area of discussion.
Correct, but that's almost no mass at all.
Okay. In terms of the Milky Way itself, the numbers that I recall in terms of its dimensions, so we get a good sense of it, is about 100,000 light years in length, about 30,000 light years in width, and the very small disk, roughly 2,000 light years in height. And what always struck me, the way to really appreciate that is to say that how long have we been broadcasting television? Certainly, 80 years, 70 years, certainly less than 100 years. And so the signals of I Love Lucy or whatever television show was in the 1950s or so, has now been broadcast about 100 years out, away from Earth. And so that's, a third of a percent of just the width of the Milky Way going at the speed of light. I mean, that gives one a grand sense of what the structure of just a simple galaxy is.
Correct. And I think Carl Sagan captured this beautifully in his book Contact, which begins with the radio astronomer receiving, the first extraterrestrial signal. And I think it's the broadcast from the Berlin Olympics, just before World War II.
Yeah.
Because that was one of the, if not the first signals to head out.
Yeah.
And that's what they repeat back to us.
So that can give you a sense of where that is coming from if you divide it, if you take the amount of years and divide it by two, simply. All right, let's move on to black holes. You mentioned it before, but let's look at, first of all, the basic structure is that before we really were sure about black holes, we knew they existed theoretically out of Einstein's equations and Schwarzschild and various other people solving Einstein's equations to show that it was theoretically possible. Oppenheimer, a lot of people involved in black holes. But now the assumption is that black holes are not just a rarity, but are actually in the heart or in the center of virtually all, or maybe even all galaxies. And that being so, the question I would have is, which way is the arrow of causation? Is it that black holes form and then they structure the galaxy? Or is it the case that the other way is that galaxies form and that leads to black holes? And I assume there's some interaction between them. But discuss the relationship between black holes and galaxies in terms of this arrow of causation.
We should differentiate between two types of black holes. There are stellar mass black holes, which are formed by the supernova explosions of massive stars. Those are tiny. Those are only a few times more massive than the sun. And then there are the monsters at the centers of galaxies, which are millions to billions of times as massive as our sun. Those supermassive black holes, we have evidence for their existence in many, if not most, if not all, galaxies, but we still don't understand how exactly they formed and evolved. It's one of the big open questions. And so when we look at first results from the James Webb Space Telescope, finding supermassive black holes that are already a certain mass, a certain number of years after the Big Bang, that's really important because that will help us, try and figure out exactly how they form. Basically, to make a supermassive black hole, you have a few ways to do this. You can either somehow get 1 million solar masses of material dumped into one tiny volume. That's your supermassive black hole. But good luck doing that, since, as we said earlier on, all matter spins in some way, and that spin helps keep it together. Okay, that's why a spiral galaxy is held together. That's why there's a disk and not a puffy elliptical galaxy. It's because the stars are moving, the gas is moving. You have to find a way to collapse all of that into your infinitesimal volume. So what we think happens is that you have seeds for these supermassive black holes that are formed very early on. And then those seeds grow into the monstrosities we see today. What these seeds are, again, excellent question. There are different models. In most of them, you have galaxies first. They develop the first and second population of stars. And it's what happens with those stars that will give you the seeds. If you have dense clusters of stars, very, very massive stars, and all of those stars collapse at the same time, you can get a seed that way. Alternatively, if you do get the infalling mass of gas to somehow fall into the center, you might get something like that.
And then how does that black hole, as it develops, in turn affect the structure of the galaxy? Does it affect the whole galaxy or just the relatively small area around the black hole?
Okay, so that's also a really good question. And again, it's a very good open question, because on the one hand, we see very strong correlations between properties of the supermassive black hole and properties of the galaxy. So for example, the ratio between the mass of the supermassive black hole and the total mass of the galaxy is roughly 1 to 1,000.
Yeah, very small.
But it's the ratio. It's the fact that it's a very constant ratio that's interesting, right? Because that tells you that these two things, the galaxy and the supermassive black hole, have to evolve together in some sense. So there has to be some kind of interaction between them.
What are the error bars around that in terms of the ratio of the supermassive black hole to the galaxy? About 1 in 1,000.
I don't know. But I think it's pretty good. It's a very precise correlation.
Yeah, that's a wonderful piece of data.
On the other hand, by their nature, supermassive black holes, like all black holes, are incredibly localized. They take up a very, very small piece of real estate inside the galaxy. Now, they do interact with the gas that surrounds them. So gas can fall into the black hole and feed it. That's one of the ways black holes grow. And as a consequence of gas falling in, some black holes launch jets of ionized particles and light, which also interact with the gas, and in extreme cases can punch through a galaxy. So this is one way where you see these jets of matter extending several galaxy lengths outside the galaxy itself.
Wow.
And so you have a lot of energy being dumped into the galaxy this way.
And these black holes, what you call active galactic nucleus, in some cases, remarkably, one can emit more light than the entire galaxy together, a trillion stars, one event like that. I mean, that strains credulity to see how that could happen, but that really does happen.
Yeah, and those things are called quasars. So, and they're called quasars because that's an acronym for quasi-stellar object.
Because people didn't know what it was.
At first, people thought these were incredibly luminous stars. And it took a while to realize that, no, there was actually a galaxy under that thing. And this is light coming not from the black hole itself, but from the accretion disk of all the gas falling into it.
And it can literally emit more energy, more light than the rest of the trillion stars in the galaxies, or however many put together.
Yes.
And how long can it do that for?
That is a good question. I do not know.
Order of magnitude. I mean, is it days or a billion years?
Years at minimum, because we have observed these things for years. But I would think much longer.
Let's briefly talk about dark matter. Very briefly, we talked about it before. But what I want to talk about is how we get the confidence level we do with dark matter. The same question applies to black holes, because it's the rotational. I mean, we only can know by a theoretical analysis or equations, but also by, most importantly, by observation. And the key observation is rotational speed of stars close to black holes or in a galaxy, and using gravitational models to see how fast they should be traveling based on the total mass involved, whether it's the black hole or dark matter. So just give a sense of the methodological way that we know the mass of dark matter and the mass of black holes, supermassive black holes.
Okay, so the key word, as you said, is rotation. And that takes us back again to what we discussed previously, right? Rotation keeps objects gravitationally stable. Dark matter was first discovered by Fritz Zwicky when he studied galaxy clusters. And he measured the rotation velocities of the galaxies in the clusters, and he found that they were rotating too fast given the amount of mass that he could measure. Basically, given the rotation speeds, they should have been flying apart. Okay, the cluster shouldn't have been stable. In order for it to be stable, it had to have 9 times more mass than he could see. And that's what he called dark matter. That was ignored for many years until Vera Rubin made her observations of the rotations of stars inside spiral galaxies. And here again, the idea is the same. Let me give an example of what you expect to see. What you expect to see is something like our solar system. You have most of the mass concentrated at the center, and then you have planets orbiting around the sun. The farther out the orbit, the lower the orbital velocity of the planet, right? The longer it takes it to orbit around the sun. That's what you expect to see. Okay?
Yes.
So you expect to see the velocity go down. But what Vera Rubin saw was that the velocity plateaued. The stars were all orbiting roughly with the same velocity instead of that velocity going down. And again, for that to happen, you have to, it's not that you need more mass in the center, it's that you need to take all of these stars, all of the galaxy, and submerge it in a halo of additional mass. Okay, so that's the halo of dark matter. And that allows those stars to rotate faster. Our sun, for example, is feeling that. Our sun is orbiting the center of the galaxy faster than it would have if there was no dark matter. Over time, as in science in general, we look for more and more ways to probe this question. Does dark matter really exist? And another way to probe this is to look for extreme gravitational effects, with strong lensing being chief among them. So one of the weird things about general relativity is that light doesn't necessarily travel in straight lines. It does so in flat space. But if something curves space, if there's a massive object that curves space-time around it, then light will travel around the object. And so stars can lens each other. Our sun can lens the light from stars behind it. But in galaxy clusters, which, as I said, contain thousands of galaxies, you get extreme effects. So let's say that I'm a galaxy cluster, my head is a galaxy cluster, and let's say that this mouse is a galaxy somewhere behind me. Okay? You shouldn't be able to see the mouse, right? My head, as massive as it is not massive enough to bend light from the mouse around it, so you don't see it. But if my head really were a galaxy cluster, then it would bend space around me so much that not only would you would see the light being bent, and because the light is being bent in all directions around me, you would see my mouse several times. You would see one image here, another here, and another roughly here. And we see that when we look at images of galaxy clusters, we see multiple images of certain galaxies.
That's the most amazing proof of general relativity, Einstein's relativity. I mean, it's really breathtaking to see that.
But it's also proof for the existence of this missing fraction of matter, this dark matter, because most of 9/10 of a galaxy cluster is dark matter, and so by mapping all of these multiple images and arcs and rings, we can map the distribution of dark matter in the cluster. And we can say there are bigger pockets here, larger pockets there. Right. It's not smooth, all of that. So it's another way that doesn't rely on rotation to show that, yeah, there's something massive here that we're missing.
Yeah, that's really important to have completely different methodologies to arrive at the same conclusion. that gives you a very high confidence level. Or what I'd like to do now is to understand how we know distances in the universe. And in your book, Galaxies, I thought this was a very clear and precise section in which you built up the so-called cosmological distance ladder. To begin, define supernova a little bit, the earlier book, because that's a critical part of what we do, and then describe this ladder going from the parallel X, which is a very high precision of nearby stars, to then sequencing through the Cepheids and then the supernova.
Supernovae are explosions of stars. There are lots of different types of stars in the universe. Well, the guiding property of a star is its mass, how much mass it's born with. And the more massive you are, the shorter your lifetime, and the more explosive and brilliant your death. And so our sun is a middling star. It will not blow up as a supernova, which is a shame. But stars more massive than about 8 times the mass of our sun will. And there are different ways for supernovae to happen. This is a field all on its own. But what's important to us is that when they explode, they emit a lot of light. That ties in to a more basic question, which is, how do you measure length in space? It's even a basic question here on Earth, right? How do you measure length here on Earth? It's pretty easy to measure your height. We have meters. But if you want to measure the distance between your house and the next, or between your apartment building and another one, you already have to use something else. You can't use a measuring tape. And if you want to measure the distance between countries, again, something completely different. The distance to the moon, we can measure with lasers. Distances to other objects in the solar system, we can measure with radar. But distances to other stars, there we rely on something called parallax. So parallax is something that you can demonstrate to yourself. You can hold your thumb in front of you and close one eye, and then close the other, blink your eyes, and you'll see that your thumb seems to jump about. And that's because we have stereoscopic vision. There's a distance between our eyes, which means that every time you close one eye, you see your thumb at a slightly different angle. The same thing happens with stars. We orbit around the sun. So let's say we look at the night sky during springtime, then we wait until we complete half an orbit. Now it's fall, and there's a distance between these two points of view. And so nearby stars will seem to have shifted. They'll seem to hop about. So if you know the distance, if you know your orbit around the sun, just as you know the distance between your eyes, and you measure the angle, you can figure out the distance to those stars. Wonderful. So now we can measure distances to nearby stars.
What's the distance that parallax, maximum distance for parallax?
I don't know the maximum distance, but think of it in light years.
Order of magnitude of light years. I mean, is it 100, under 100 or something?
I think it would be under 100, because even within our own Milky Way, I think there's a limit. Okay. So now we have the parallax, something less than 100 light years, which is let's say with parallax you can measure the distances to stars within a single galaxy.
Okay.
That's the important point. So now, if you want to measure the distance to another galaxy, say Andromeda, you need something else. And so here we start looking for what we call standard candles. So we want objects whose luminosity we understand. Well, luminosity is the amount of light an object emits. Okay, there's a difference for astrophysicists between luminosity and brightness. Luminosity is the amount of light an object emits. Brightness is the amount of light from an object that we receive here on Earth. Let's say we have two objects that have the same luminosity, but one of them is nearby and the other is far away. They emit the same amount of light. But here on Earth, we receive more light from the nearby object than from the distant one. And so the nearby object seems to be brighter. We can measure the difference in brightness. And we know that the two objects emitted the same amount of light. So we know the brightness, we know the luminosity. The only thing missing is what connects between brightness and luminosity, which is distance. Okay, and so that's how we get a distance. So now we need such an object. Okay, and the first such object is a type of variable star called a delta Cepheid. All stars pulsate. It's like they have a heartbeat. And so they slightly expand and contract, expand and contract. Our sun does that, but not so much that we would notice, in our daily lives. Very massive stars go through periods where they have huge pulsations. So much so that the luminosity goes up and down in a very well understood way. In these stars, the periodicity of the changes in luminosity is related to the difference between the low point and the high point of the luminosities. And this was something that was figured out by Henrietta Swan-Leavitt, one of the famous Harvard computers who worked at Harvard Observatory at the beginning of the 20th century. So now we have these, and Edwin Hubble famously used observations of Cepheids in the Andromeda, then called the Andromeda Nebula, to measure a distance to that nebula and realize that it had to lie outside the Milky Way. And so that had to be its own galaxy. So now we have a way to measure distances to other nearby galaxies. But Cepheids are limited, okay? They're only thousands of times as luminous as the sun. So if you want to go to really distant galaxies, you need a new standard candle. And that's where supernovae come in, specifically type 1a supernovae. When they explode, they are millions of times as luminous as the sun. And so you can see them much farther away. But so what you have to do, you have to build what we call a cosmological distance ladder, where each rung on the ladder is a different standard object.
And what's most significant to me is that you have an overlap between them, between the parallax and the Cepheids, and then the Cepheids and the supernovae, so that you can calibrate each one. It's not like they're totally separate, so you have to analyze each one, but you can calibrate one by the other. And since the original one is a parallax, which is the strongest proof, because as you said, you can do it with your thumb, so you know that's real, that if you can confirm the Cepheids with the parallax and then the supernovae with the Cepheids, you really have a strong ladder.
Correct. Now, I wouldn't be an astrophysicist without saying that you can, I would say, except for parallax, you can attack every other rung on the ladder.
There's always dust. There's always
dust. We still don't understand how type 1a supernovae explode and whether they evolve with redshift. There's a lot. Okay. And the distance ladder that we just described is only one such ladder. There are others using other types of standard candles or other techniques to estimate luminosity.
And again, you get different methodologies, like the cosmic microwave background is another totally different kind of approach, which to build a cosmological distance ladder.
Well, not to build a cosmological distance ladder, but to get at the nature of dark energy and dark matter. So the reason we build these ladders, well, one, it's fun. But two, it's also to understand the way in which the universe is expanding and has been expanding for the last 13 billion years. And so it's from the use of type 1a supernovae as distance, as standard candles, that we discovered that not only is the universe expanding, but that expansion is accelerating.
That was the big discovery in 1998 that totally revolutionized. But by articulating the expansion of the universe through the cosmological distance ladder and through the cosmic microwave background, two different ways of doing it, you increase the confidence in the results of both.
The distance ladder that we've built out of parallax Cepheids and supernovae is one way to measure the expansion rate of the universe. There's another way to do this by analyzing the cosmic microwave background, the light that was emitted when the universe was only about 400,000 years old. So these are two completely different ways, different methods that probe the universe at very different stages of its development. The CMB is the very early universe, while the supernova distance ladder is the late universe. It's what we see now nearby. When you do this, when you measure the expansion rate this way, you get two measurements that are very, very precise, meaning they have very, very small error bars, around 1%, and they're very close to each other. One is about 67 kilometers per second per megaparsec, and the other one is about 74. And you would say to yourself, okay, it's pretty much the same thing. But the error bars are so small that the difference between these two values begins to become suspicious. And this is now what has become known as the Hubble tension, or the new Hubble tension, where we try to understand why these values are still different. And the short answer is we don't know yet, but there might be some new physics involved.
Yeah, that would be remarkable if that were the case, and that there's certainly a debate about that, whether there's some structural reason why this is occurring, like we found sometimes with dust that creates distortions in our view. But as you said, it's been going on for how many years? A couple of decades or so, and the problem's getting worse because the error bars are getting smaller.
Yeah, and we search for new ways to measure the Hubble constant, and we still, the tension isn't going away. But that's good.
Yeah, that's good. That's good. Of course, anytime we can disprove things that we thought were right, we learn more. All right, so now we're going to do some very short questions, very short answers to very big questions. So it's exactly the opposite of what we were doing before, is really analyzing stuff. So this is just your superficial kind of reaction to a lot of crazy questions. So my first one is based on your work in galactic formation. How would you react to the big theories of cosmic creation? And I'll list a few. We have, cosmic inflation, Alan Guth's or Andre Lindy's eternal chaotic inflation. That's sort of one category. Another category is the so-called big bounce ekpyrotic universe. Paul Steinhardt has talked about that. Another is the Hartle-Hawking no boundary universe, where there's a rounding and there's really no beginning to time. It all becomes space in some way. And then, of course, Roger Penrose has something completely different with a conformal cyclic cosmology. Does the hard data of galactic formation lend support or falsification or approaches to any of these big theories?
Not yet.
Okay. Is it possible that it can? In other words, is sufficient information about galactic structure and formation, is it the kind of thing that could answer these questions?
These questions will be answered once we understand dark energy.
Let's go on to some other question of Of all the models of the universe in terms of structure, what's your current favorite? You're allowed to change your mind when we talk again in a few years.
I really don't have one.
Okay.
I really don't.
Okay, spoken as a true experimentalist. Um, okay.
I never trust the theory. I mean,
The laws of physics, is it immutable or can they change? This is an important factor in a lot of the conversations we're talking about, because some of these anomalies, some people say, are caused by a change of the laws of physics, like modified gravity.
modified gravity is not a change in immutable physics. Usually that means a change in the value of certain constants. We have no observational evidence for any such change.
Do you think the laws of physics are necessary, chance, or brute fact?
I think the laws of physics are not laws. They are a mathematical construct that we use in order to describe the world around us. They work for us at the moment. They may no longer work for us 100 years from now or 1,000 years from now.
Okay, so we like to call them regularities that we now see irregular, which might have some changes in the future, but that reflects on our understanding as opposed to the regularities themselves.
No, it's something more basic. Physics is a language that we use to describe the world, just as we use language to tell stories.
So the universe, order of magnitude, may have a 10 to the 22nd to the 10 to the 24th number of stars in the observable universe, at least as many planets. So in your view, how would you answer three questions? The prevalence of simple life, the prevalence of intelligent life, and the prevalence of intelligent technological life that could be identified. And this is, of course, the famous Fermi paradoxes. Obviously, we don't see anything.
We exist, ergo, simple, intelligent, and advanced life can exist. If we exist, why shouldn't more life exist? We're not special. Are there other life forms out there existing alongside us now? I don't know.
Okay, last question. The two books that you had each had wonderful one-word titles, Supernova and now Galaxies. Do you have a third in mind, maybe multiverse?
What I'm writing now is a book about the multicultural mythology of the Milky Way, which alliterates very, very nicely, but doesn't condense to one word.
Well, Milky Way, that's two. That's pretty close. Well, it's been great, Or. I really enjoyed our conversation. Love the book, Galaxies. I recommend it for everyone. Viewers can watch dozens of TV episodes and hundreds of exclusive videos on cosmology, galactic structure, on the Closer to Truth website and the Closer to Truth YouTube channel. Thank you, everyone, for watching. And Or will get back when your next book is written, and maybe we'll have some further knowledge about the structure of the universe and the Hubble tension.
I look forward to talking to you again. Thank you.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.